Hi everyone, in this video we continue learning about functions, and specifically we're gonna talk about what's called function notation, and we'll do a few examples related to functions. This is how function notation looks like. It can be used to replace the variable y, the variable that denotes the output of a function, which means that the entire notation also represents the output. But let's look closer at the notation itself. Here we have two letters, f and x. Keep in mind that there is no multiplication operation going on here. This is just one notation. Specifically, the first letter, f, represents the name of a function. F is the common name because it stands for a function, but we can use any other letter. And then x inside the parentheses represents the variable of the input. So far we said that variable x is used for the input and variable y is used for the output. And yes, these are the two most common variables. However, other letters can also be used for both input and output. And we read this notation f of x. And here's an example. Function f of x, f is the name of this function, equals x squared minus 1 over x plus 4. And we already know that this expression tells us how to get an output for each given input. Let's do a few examples to practice the function notation. In this example, it says find the following for the above function. So that's the function that we're going to use. And what we need to find is this. How do we read it? Again, we're going to read it f of 5 this time. So in general, it's f of x. Here it's f of 5. And we need to find what that equals to. Now, since 5 stands inside the parentheses, it represents a specific input. In other words, it represents specific x value. X equals 5. And this means that to find what f of 5 equals to, we simply have to plug 5 into the function. Let's try that. So to find f of 5, we replace each x in the function with 5. So in the numerator, it's 5 squared minus 1, and then in the denominator, it's 5 plus 4. Now let's simplify. 5 squared is 25. 5 plus 4 is 9 in the denominator, so we get 24 over 9. And we should be able to simplify this fraction if we divide by 3 on the top and on the bottom, so that's 8 over 3. So in other words, f of 5 equals 8 over 3. And again, 5 represents input. And the function value, what we found, 8 over 3, represents output. We show it here, right? It's the same as the y value. Now the next step is not required, but I want to write it down to better understand the result we obtained and just to refresh what we learned before. So if we know that input 5 corresponds to the output 8 over 3 for this function, we can put them together as an ordered pair. 5, 8 over 3. Let's try another example. We're still using same function. However, this time we need to find f of x plus 1. Once again, there is no multiplication here. All of that is the function notation, f of x plus 1. How do we find it? This time inside the parentheses we don't have a number, we have an expression x plus 1. Well, but idea stays the same. Whatever inside the parentheses represents an input, which means that it has to be plugged in for x. And the only difference is that last time we had to plug in number for x. But this time we have to plug in an expression. In other words, every x in this function, there are two places, has to be replaced with expression x plus 1. Let's write this down. F of x plus 1 equals the first x in the numerator I am replacing with x plus 1. And because x is squared, expression x plus 1 is being squared as well. And then I continue the numerator by writing minus 1. In the denominator, I am replacing x with the given expression x plus 1. And finish this off by writing plus 4. So that's what means f of x plus 1. And what's left to do is just to simplify this expression by simplifying the numerator and the denominator. In the numerator, I will square expression x plus 1. Remember, the correct way to square any expression that involves several terms is to write that expression twice, x plus 1 times x plus 1, and then FOIL. So here I have to write minus 1, and in the denominator, I can drop the parentheses. It's x plus 1 plus 4, so I can collect like terms. Going back to the numerator, I will have to FOIL those two expressions, the binomials. This will give me x squared plus x plus another x plus 1, and then minus 1 over, well, x plus 1 plus 4. 1 plus 4 I can add, so it's x plus 5. Okay, and now finally combine like terms. It's going to be x squared plus 2x, and in the denominator it's x plus 5. So f of x plus 1 equals this expression. And let's do one more question with that function. So this time we need to find f of negative 4. The input is negative 4. Let's plug it in and see what happens. I'm replacing x with negative 4 in the numerator and in the denominator. And as I start simplifying, I can see that in the numerator it's going to be negative 4 squared, that's 16. 16 minus 1, 15. And then in the denominator, I get negative 4 plus 4, that's 0. What can we say about this result? Well, it's undefined. Every time we have 0 in the denominator of a fraction, in other words, we're attempting to divide by 0, the result is undefined. We cannot divide by 0. And I added a reminder here just in case someone needs to refresh this. So yeah, when we have 0 in the denominator, the fraction is undefined, and if we have 0 in the numerator, well, then the result is 0. Going back to our answer, let's think what it means. So we're trying to evaluate f of negative 4. In other words, we're trying to find an output for the input negative 4, and we didn't find it. The result was undefined. So that means that for this function, input negative 4 does not produce an output, and therefore we cannot use this number as an input. And the reason this happened is because, well, negative 4 created 0 in the denominator. Can anything else go wrong with this function? Well, not really. So with 0 in the denominator, that's the only undefined case. And negative 4 is the only number that produces 0 in the denominator, right? So that means that any number that we choose for input will produce some kind of output except negative 4. And that's exactly the domain of this function. And this is how we can write it. Domain is represented by all real numbers except negative 4. Here's another notation that can be used to represent this domain. It's called set builder notation. The way we read it is this: all x such that vertical line represents such that x is not equal to negative 4. And here is one more notation. It's called interval notation. Basically, to describe all real numbers without negative 4, we have to use two intervals. One that goes from negative infinity to negative 4. Notice that we use parentheses here. It means that negative 4 is not included in this interval. And the next interval starts at negative 4, but negative 4 itself is not being included because of the parentheses. So from negative 4 to the positive infinity. And negative 4 itself, again, it's not included in either one of those two intervals. This is the union notation, which means that those two intervals together represent the domain of the given function. But we're going to continue practicing the function notation, this time using the graph. Here is the given graph, and we need to find f of negative 3. Again, we remember that negative 3 inside the parentheses represents an input of this function, or the x value. We need to find what f of negative 3 equals to. In other words, we need to find the corresponding output or y value. And as you can see, we're only given a graph of the function. By the way, try to use vertical line test to confirm that's a function. And as we already learned, we know that this curve contains all possible inputs and outputs of the function. So to better understand what to do, we need to rephrase this question. So to find f of negative 3 using the graph, we need to find a point on the graph that has x-coordinate negative 3. And the question is, what's going to be the y-coordinate of this point? Let's see. So x equals -3 on the number line is here. Let's project it, in this case, down to the curve. And let's see where we hit the point that has x coordinate -3. It's right here. Now, what is the y coordinate of this point? It's -2. So that's the point -3, -2. And this means that input -3 for this function corresponds to the output -2. And that means that f of -3 equals -2. Let's try it one more time. We need to find f of 4. Again, 4 represents the x. And we need to find a point with the x coordinate 4 and check its y coordinate. So let's find 4 on the x-axis. It's right here. Let's go straight up to hit the line. Notice that the endpoint is closed here and it's open here. So that means that point on the graph that has x coordinate 4 is this one. What is its corresponding y coordinate? Well, it's 3. So this point has coordinates 4, 3, and since this point is on the graph, it represents relation x equals 4, y equals 3 for the given function. So the answer to the question, find f of 4, is going to be 3. Now let's switch things around, and for the next question, let's try to find all x for which f of x equals 6. Notice that this time we're not given x. We don't know what x is. We need to find it. But we know the function value, f of x equals 6. So function notation, f of x, it's another way to represent y, or the output. So in other words, we're given the y value this time, and we need to find the corresponding x values. Well, since we only have a graph, again, we're going to use points on the graph to answer the question. This time we need to find a point such that its y coordinate is 6, and our goal is to find the x coordinate. For that, we're going to find 6 on the y-axis here, and we're going to go straight to the right. I'm going to project that to the graph. Here's the point that has the y coordinate 6. What is the x coordinate? Let's go straight down, and looks like it's also 6. So this function has an ordered pair, x equals 6, y equals 6. How do we write the answer? It says find all x for which f of x equals 6. We can simply say x equals 6. Or we can also write the answer using function notation. We can say f of 6 equals 6. Let's use this graph to practice a few more things. Let's try using this graph to determine the domain of this function. Let me remind you that domain represents all possible inputs of a function. Now, this time function is given in terms of the graph, and all inputs are simply the x-coordinates of the points on this curve. So we just need to look at this graph and understand what are those x-coordinates of the points on the graph. So if we scan this graph from left to right, what is the leftmost x-coordinate we can observe? Well, it seems like it's -4. However, -4 itself is not going to be coordinate because we have the open endpoint here. But any value after -4 will represent an x-coordinate of some point on the graph. So basically, one way to determine domain when you have only the graph is by projecting points from the graph on the x-axis and observing what portion of the x-axis is being covered. So if I try to project all the points from the graph down to the x-axis or up to the x-axis, then what portion of the x-axis is going to be covered? Let me try to highlight it. Once again, we see that everything starts at -4, even though -4 itself is not included. It's not the x-coordinate of any point on the graph because of the open endpoint. But all values after that will represent the x-coordinate of some point on the graph. And notice that we have an arrow here on the right-hand side. So that means that this line continues and we can project more and more points to the x-axis. So this highlighted portion of the x-axis will continue as well. How can we describe what I've just highlighted? Well, it's an interval that starts at -4, even though -4 is not included, and continues all the way to infinity. I can use the interval notation to write this down. It's the interval from -4 to infinity, but -4 itself is not included. That's why I'm using parentheses here. To summarize what we just did, I'm going to say that when you need to determine the domain of the function, if you have the graph, then think and describe all possible x-coordinates of the points on the graph. And next, let's try to determine the range of this function, again using the graph. Well, range represents all possible outputs of a function. Outputs are represented by variable y. So we're going to use the same method and focus on all possible y-coordinates of the points on this graph. I cleaned my picture and now I'm ready to think about the y-coordinates. We're going to scan the y-axis this time, of course. When we scan the y-axis, we always go from the bottom up in the increasing direction of values on the y-axis. So what is the lowest point on the graph and what is its corresponding y-coordinate? Well, again, the endpoint is open here, so it's not really a point, but it's at -7. So we'll start seeing points right after that. Using interval notation, we will write -7, but we'll use parentheses to indicate that -7 itself is not included in the interval. And as we start moving up and we project points from the graph to the y-axis, we can see how this portion of the y-axis will have corresponding points. However, as I move further up, here I notice a gap, so nothing from here will project to the y-axis. So I will have a gap and I will pick up from here. Again, at 5, I don't have point, it's open. However, everything above 5 will represent the y-coordinates of various points on the graph. We talked about this arrow, how it indicates that the line continues. So it means that I can project more and more points to the y-axis moving up. So I can see how the rest of the y-axis will be covered after 5. So let's describe what we have observed. So it looks like we have two separate portions of the y-axis that represent the y-coordinates of the points on the graph and therefore will be part of the range. The first portion starts at a number that's very close to -7, but not -7 itself. So on the interval notation, we'll just use the parentheses here. And then it goes up to 3, where 3 itself is included. We do have a point at 3. And then the second portion starts at, well, very close to 5. We'll say 5, but we'll use parentheses to indicate that 5 itself is not included. And then it continues 5. Numbers keep growing, so it goes to positive infinity. Let's write this down using interval notation. So the first interval is from -7 to 3. And then we have to use union here because we have another piece. And that's the interval from 5. I'm using parentheses because 5 itself is not included, to positive infinity. So these two intervals represent the range of the given function f. And at the end of this video, we're going to do 2 more questions where we need to determine the x-intercepts and the y-intercepts of the function. Basically, the x-intercepts of a function are points where graph crosses the x-axis. How many points like that can you find? I found 3 here at -2, at 0, and at +3. So that's where the graph crosses the x-axis, and therefore these points are called x-intercepts. To write down the answer, we can either list the x-intercepts, -2, x equals -2, 0, 3, or we can use the ordered pairs. In this case, we neutralize that the y-coordinate of each point is the same, and it's 0. So the first point is -2, 0, the next one is 0, 0, and 3, 0. So no matter what graph you work with, the x-intercepts will always have y-coordinates 0. Next, let's determine the y-intercept. Keep in mind that function can only have one y-intercept. Think why. The vertical line test will help you to find the answer. Now, what is the y-intercept? It's the point where the graph crosses the y-axis. Do you see it on the graph? Well, it's right here. For this specific function, the y-intercept and the x-intercept happen to be the same point. It doesn't have to be like that every time. So basically, that's the point 0, 0. That's the y-intercept.